Okay, we've got another geometry induction question, which says prove by induction for integers n greater than or equal to 1, n lines in the plane, no 2 being parallel and no 3 being concurrent, divide the plane into that many regions. Okay, so no 2 of the lines are parallel, and concurrent here, no 3 are concurrent means that no 3 meet at the same point. Okay, so if you're concurrent, you meet at the same point. So that means we're not going to have a situation where I see 3 lines all intersecting at the same point. So that's not allowed. Alright, I think now we know what we're after. Let's just start. Okay, so lowest value of n would be n equal 1. So let's start our induction by testing n equal 1. Okay, so if n equal 1, convince yourself that if this is your line that goes on forever in both directions, there should be 2 regions there. So when n equals 1, there is 2 regions. So let's check the formula. If I sub in n equal 1 there, hopefully we get, that's going to be 4 divide 2, which is 2. Okay, so therefore true for n equal 1. Okay, let's assume true for n equal k. So that means that k lines, I'm just going from the question here, divide the plane into half, I'm just changing the n's to k's, k squared plus k plus 2 regions. Okay, and now we need to prove true for n equal k plus 1. So RTP is that k plus 1 lines divide the plane into half, and then I'm going to change those to k plus 1s. K plus 1 squared plus k plus 1 plus 2 regions. Okay, so that's what we're required to do. Alright, I think the way to go about it is it's all in the diagram and working out as you go from the kth case to the kth plus 1 case, how many extra regions are going to be formed and how are those regions going to be formed. So let's just start by we'll start from one line. We have 2 regions. Convince yourself that the second line that I draw, I can't draw it parallel. At the beginning here, it already introduces 1 extra region, and then on the other side of that intersection, we get another extra region. So the second line, it crosses 1 line, and the key thing it does is it adds 2 regions. Okay, whoop. I'll go over here. The second line crosses 1 line, adds 2 regions. Let's see if we can form a pattern. So I need to do a third line here. So let's draw a third line. It can't be parallel to those 2, and it can't be concurrent. So it can't go through. So we've got like that. Okay, so now let's have a think here. Over here, we create another region. Over here, we split that into another region. And over here, we create another region. So convince yourself that the third line, it crosses the 2 lines and adds 1 region, and 1 region, 3 regions. So it seems like the pattern is that if I can continue this pattern, this whatever line I'm adding seems to add that many regions. Okay, so I guess if I'm adding the kth plus 1 line, it would be that the kth plus 1 line crosses k lines and adds k plus 1 regions. Okay, every time you cross a line, you introduce a new region. Every time you cross a line, you introduce a new region. And I guess the extra plus 1 would be at the beginning. You start a new region even before you've crossed any of the lines. All right, so the key thing seems to be that we're adding k plus 1 regions. The k plus 1 line will add k plus 1 regions, and hopefully that will get us to where we need. All right, so let's see how we can draw this. So let's go k lines. Okay, let's just do a random drawing and let's pretend that's k plus 1 lines. You would have the same, all these lines. Okay, I'm going to put arrows, trying to redraw the same picture. And then we're going to add, maybe I'll draw an extra bolded. Maybe I'll make it so that it's clear that it eventually, because it's not parallel to any of the other ones, eventually it'll cross all of them. So let's try and draw something that will cross all of them. Oop. Let's try again. So I'm going to call that the k plus 1 line, the extra line that we've added. So the k plus 1th line will intersect the other k lines, causing an extra k plus 1 regions. Okay. To form. So therefore k plus 1 lines will divide the plane into from the assumption it'll be half k squared plus k plus 2. And then we're adding an extra k plus 1 regions. And I'm going to say from assumption. All right, so I need to show that this expression here is equal to this guy here. So I might take out a common factor of a half. Essentially times 2 divide 2, so I can take out a half there. It'll be k squared plus k plus 2 plus, and that'll be 2 bracket k plus 1. Okay, I need to now try and get it into this form. If you like, you can expand this guy and collect like terms and show that it will give you the same as this. I'm going to go about expanding, and I'm going to do a complete square. I'm going to complete the square, 2k plus 2. So it's a half k squared plus 2k. Now I'm going to do plus 1, so that's a perfect square. And then I've got a k plus 1. So I've done that, I've used one of that. Now 4, I should still have a plus 2. I've used that. Okay, I've used up everything. Alright, so that equals to a half, and now I can complete the square. K plus 1 all squared plus k plus 1 plus 2, which equals as required. And then finish the induction by saying, therefore, if true for n equal k, then true for n equal k plus 1. Therefore, by the principle of mathematical induction, the result is true. Okay. The key thing was spotting the pattern. As I add an extra line, okay, it's going to intersect with every other line that was there previously, which would be k lines, and then divided into k plus 1 planes. And I think if you're not sure, start a pattern, just like how I did over here. I started a pattern with one line and I added another line and I saw what happened, and then I added another line, I saw what happened, and I could sort of see the pattern that was being produced. And a good geometric proof has a good diagram and a brief explanation after explaining. All right, so that's that question.